So yesterday, before I say something, right now we have 5 applications using this TP formulation. The last one is a fluid structure interaction, but to include here is not very good because it really takes a complete separate 1 hour talk, so I just skip that part. So the first one is obviously, since I'm a dynamicist, apply to dynamics problem, and then use the same equation as I showed very briefly yesterday, the iterative algorithm for quasi-static problem. And then the component model synthesis, otherwise it's now known as labeled as a reduced order model. And we are just beginning with the structural system, but I'm very much interested in any one of you guys are interested in reduced order model using this TP formulation for coupled system, because that's where the reduced order modeling challenge is. And then finally, the damage detection in big infrastructure, such as a nuclear power plant, is a very, very important problem. And finding out from collecting the sense of finding out where damage might be occurring or occurring now is really very important problem. So we are just starting some of this. Then I'll go over with you one by one. So these are the 4 problems. And the Professor Gonzalez is with the University of Sevilla. I call university, but he calls us some engineering different name, which I don't remember. And Kim Hyun-jun and Young-Hwa Park is at KAIST, and Seung-Won Kang and Shin Hyun-jun is at Seoul National University, and Mr. Park Ki and Professor Kim are in Kyunghee University. Okay, so let me just recap what I mean by TP equation. You don't assemble it. M is a block diagonal, K is a block diagonal, and PD is a projection operator, where PD consists of 2 things. One is identity, means K itself. And then PC times KD is the one representing interface force. So instead of interface force, Lagrange multiplier, you replace that with the PC times KD. And when M is a diagonal, then MB, MF is all diagonal. Okay? So there's very little computational effort to generate this equation. B is the most important quantity, that is, it really identifies where the interface degrees freedoms are for each partition. And I have written something like a 10-line code that really generate from the assembly operator LG, where LG is related to assembly degree freedom to partition displacement. In finite element code, the way you are using, you don't see this because the finite element right now, the way that 99% of the coders are using, they are doing this one directly. So you put one element, and then the next element, either you put over here, or you put over there. So you don't really see LG because it's done explicitly. Okay, but in your code, what you will see is for global nodes, you have this global node number. There's an element number, and there's a nodal number over here. And for each element number, how this element is connected to the degree of freedom. Okay, that's how you assemble. And in the same way, if you use this connectivity table, you can create LG automatically. It's 1, 0, 1, 0, 1, 0. Okay. So it's a very simple thing to generate LG. So that's the governing equation. So you see, this is coupling the these are the coupling matrix when you use a conventional thing, but still in the DP formulation. So the PD actually brings a necessary coupling, but PD is not doesn't require anything other than diagonal mass matrix. And everything else is a Boolean number, either 1 or 0. So in first thing what we did was put the PC times KD on the right-hand side, and you predicted this guy, and then you integrate this part by implicit integration. You only need the factorization of this, this, and that. So it's a block diagonal factorization. It's very efficient. It doesn't matter whether you have 100 or 1,000 partitions. And this is done on a vectorial fashion. Okay. Do I have to aim something?
He's running out.
I have to. Oh, okay. Ah. I put here something. That's not working. You can just open. Okay. Oh, thing didn't come out right, but it's okay. So, okay. So this is the implicit part. This is the forcing function, and this is the explicit part. So when you use a midpoint rule, you integrate using this part. But the midpoint rule is something not many people are using it, but it doesn't make any difference whether you use a trapezoidal rule or Newmark algorithm or not. For linear problem, for non-linear problem, it doesn't make a huge difference. Okay, and there are papers about that. So since we are ultimately trying to use this, we are using midpoint rule. In other words, we advance half the step, and after we solve it, and then we get the full step by extrapolation. And then you update the acceleration and update the velocities. So when you look at the P, which is on the right hand side, this is AX equal to P. There is this term shows up, and this is known forcing function, and this is actually n plus half what we are really extrapolating with the previous step size. So that's basically essence of implicit, explicit transient algorithm using DP formulations. I mentioned a little bit yesterday because Eugenio asked about it. See, there's a very important finite element dynamic properties. That is, the maximum eigenvalue of element eigenvalue of all the elements, the maximum elemental eigenvalue is the upper bound of the assembled maximum eigenvalue. Okay? So what that means is very important. That is, by treating elemental or substructural system by implicit algorithm, you are actually guaranteeing stability with respect to the maximum partition eigenvalue. Okay? There's no step size restriction. So this guarantees that this implicit explicit algorithm is unconditionally stable. Of course, for those of you who are more mathematically aligned, the previous explanation is enough. You can actually eliminate all the velocity acceleration by the finite difference equation in time, and then look for Dn plus 1 is some lambda times Tn. When the lambda is mapped on the G plane, in other words, Tn plus 1 will be lambda Tn, where lambda, in order for this system to be stable, the magnitude of lambda has to be less than 1. Otherwise, it will blow up. Now, so this is 1. So this is a lambda plane. If you map this guy to Z plane by lambda equal to 1 plus Z, 1 plus G, 1 minus G, for lambda, absolute value lambda 1 maps onto the left-hand plane. So I use that formula directly. So this is the amplification factor from Tn to Tn plus 1. And Tn is a Tn minus 1. You can express everything in terms of Tn minus 1. You find out that S times Tn minus 1 equals to 0. And S turns out to be this value, which is a quadratic function of matrix characteristic function. And there's a root-Hurwitz theorem, okay, which is used in control community a lot. That says M is a positive definite. This is semi-positive definite. This is a semi-positive definite. In that case, there's no negative sign over there. Therefore, the S has the eigenvalue in G eigenvalue, which is less than 0, which means they are all mapping on the left-hand plane, which means lambda is equal to 1 or less than 1. So therefore, the implicit explicit transient algorithm that I described is unconditionally stable. The accuracy, I'm not gonna spend too much time on it, except what you wanna say here is, if you really assemble, this is a partition equation. If you assemble this one, what that means, LG transfer PC is 0. So in the G equation, in other words, we are back to the assembled equation, the notion of extrapolation goes away, and therefore it's unconditionally stable. That doesn't mean we have a full accuracy of assembled system at all. So this is just difference equation, and one nice thing about it is if you expand this thing in terms of a Taylor series, you say, sorry, I don't know, something didn't turn out to be right. When you converted it, I think. Oh, yeah, do you want that? Yeah. What it does is, up to the second order, it matches Taylor series expansion, and only in the third order, in order for this thing to have that, it has to plus delta t's cube over 12, this quantity. But there's an obviously error, which means this is only second order accurate. It's not as accurate as a fully implicit method either, which shows up now. This is really one important is when we derive the DP equation, the constraint condition was a momentum conservation between the interface and the partition, or acceleration for that matter. We did not use a displacement constraints. Since this is second order system, realistically, to satisfy in terms of Hamiltonian dynamic, you need to satisfy two constraints, either one acceleration velocity, or acceleration displacement, or velocity and displacement constraints. Okay? The reason is this is something, since we are talking about the detail, when you change this thing into a canonical system, you have x1 dot is, so when you take a canonical system, it becomes a 2x2 matrix. So assuming majority of you guys are students, our velocities and accelerations are independent or dependent? Is it yes or no? For those who think it's velocities and accelerations are independent, raise a hand. Or dependent, raise a hand. So velocities, accelerations are dependent. Wrong. Now, velocity, acceleration, velocity, displacements, the three variables, they are dependent. They are only rank of 2. Okay. Otherwise, Hamilton would not have succeeded, because what he did was since this is I don't have to finish all of that, but I want to say something very important. So if I have here is x1 is x, x2 is x dot, and if I day x1, x2, then I have this, okay, and this becomes x2. So I have here identity x1 dot, x2 dot, right? And I use this one is x2. There's minus 1, 0 is equation. That equation is bringing in from here is a minus x, okay, which is x1. So here's a 1, 0. Equation like that. Now, this is rank 2, right? Identity matrix. Determinant of this guy is 0 or no? It's 1. Which means this equation has a rank 2. Which means x1, x2 are linearly independent. Or x1 dot, x2 dot are linearly independent. Okay? So if you forgot all my other lecture material, please remember that. This is, if this is not the case, Hamilton would not have succeeded in presenting. All Hamilton did was use this equation in astronomy in terms of 2 first order equations. And the way he could do that was because velocity accelerations are linearly independent. And displacement velocities are linearly independent. Otherwise, you cannot put the second order system like that in terms of canonical system. Okay? So if you forget all my lectures, just remember this. By the way, you're not the only one. About 30 years ago, when I was a little bit more active, I belonged to both the ASME and ARAA Dynamics Committee, and I chaired both sections for a while. I made the survey. The other university professors and the researchers, okay? The other and the committee members, about 32 guys. Are they independent or dependent? Only 60% of those who are teaching dynamics, doing research, said that they are linearly independent. Yeah, I said, no wonder you guys don't use Hamilton's equation. Okay, so let me get back to the. So since we are not we satisfy this, we are not satisfying this. We have to enforce this. Okay, in dynamics as well as statics. So we do T is deformation and rigid body mode. And the deformation, leave it there. I can, once you know the partition rigid body mode, you can write generalized solution like that. And then you substitute into this displacement constraint. And you can reduce this Ti by another projection, PR. And you can find out T filtered, which means satisfying this constraint. turned out to be solution of D. We just show that one, and subject to this projection operation. Then this constraint will be satisfied. Okay. I gave this task to one of my PhD students. Sometimes I test the students, see whether they can figure out themselves something. And after about 9 months, he still could not figure that out why there was a problem. So I finally had to tell him, this is what you do. Normally, if the student figure out, I let them figure out, even if it takes time. That's how you guys learn. So without that satisfying displacement claim, it will go like this. After that, all I have is a phase shift. But if I reduce the degree of freedom, you see like 1/3 of that follows pretty much the fully implicit solution. And still it's very efficient because in terms of central difference algorithm is something like about 200 times the step size. So we are now working on how to come up with a more accurate solution. And this requires phase filter, not the amplitude filter. So we are working on to develop a phase filter to improve the errors associated with this. So there are two kinds of filters. One is an amplitude filter, and there's a phase filter. And in the end, you can solve all the horrendous dynamics problem by just by implicit explicit solution using just a block diagonal solution matrix. The second problem is, since even though I'm a dynamicist, I have to accept the fact that in engineering practice, 80%, not in aerospace, but in civil engineering in particular, 80% of the problem we are dealing with are static or quasi-static. So we wanted to apply this DP equation for quasi-static problem. Nice thing about it is, for quasi-static problem, M doesn't have to be physical mass matrix. M can be anything actually. M can be the best possible dynamic relaxation mass matrix, for example. Okay. We are still exploring some other possibilities. So this is just without the iterating. You can sort of directly using this equation. One amazing thing is, this is the same filter I used in the dynamics. Is once we don't have to use an iterative solution. There's a direct solution. Once we have this deformation solution with the generalized unassembled matrix, you can get the displacement automatically. But that's not very nice. So what we do is we put it in the residual form. Okay. And then we apply some various kind of preconditioner. A is a preconditioner. And then you use any iterative solution. And the most popular one is conjugate gradient technique. This is a thing called the pre-condition conjugate gradient technique. This is the one that I showed you yesterday. So blue is DP solution without regularization. It doesn't converge because it's very heterogeneous. With the regularization, it goes like that. And there's a fat T or a fat T. In this case, it doesn't make any difference. Fat TDP doesn't make any difference in this particular example. Without regularization, same as a TP iterative solution, it doesn't really converge. The DP does converge after so many iterations, something like 20, which is ridiculous. But fatty without regularization doesn't converge. With the regularization, it does converge, but this is not the residual norm. This is a displacement error. So the DP with the appropriate preconditional gives you much higher accuracy than fatty in this case. The reason is, as I said yesterday, we are solving for the displacement, whereas in fatty, you are solving for interface force first, and then use that for interface force to get the displacement. And for heterogeneous system, there's a problem associated. Like anything else in iterative technique, it's very important to have a what I call fundamental solution. Fundamental solution is really rigid body-like solution. Okay, in statics, the basic equilibrium equation. And that you can obtain this way very simply. With the PRC given by that. So we get fundamental solution, and then all the subsequent iterations, you get the increment correction that has to be orthogonal to this displacement. Okay, that's the nature of an iterative technique. And this is an algorithm. And so here is heterogeneity is pi is 10 to the 6. So the difference is 10 to the 6. Because 10 to the 3 minus 3 and 10 to the plus 3. So difference is high. The heterogeneity is 10 to the 6. And again, we try two different preconditional. This thing doesn't really work as nicely as just using just generalized inverse block diagonal generalized inverse, which is very cheap. And it does require a little more iteration, but it achieves a high accuracy. That's for the homogeneous case. In heterogeneous case, that's different story. In heterogeneous case, we beat those guys. This is fatty. And heterogeneous cases, we found out this particular preconditional is much better than the K generalized index. So we are still learning, but it's a three-dimensional problem. Three-dimensional problem. Number one, to the best of my knowledge, no domain decomposition solvers are scalable. There's none. We don't know whether DP iterative solution will be scalable or not. Okay, but we are hoping that we might be able to show. I have 3 mathematicians right now working. Prove that to me whether the DP formulation for 3-dimensional problem would be scalable. If it is scalable, it's a huge thing. So I'm very hopeful that even if it's not completely scalable, so much scalable, still is a huge success using DP formulation. So I have 3 applied mathematicians are working on proving whether this would be scalable. I don't have time for that. So this is a homogeneous case. Again, Fetty does better than the DP formulation. On the other hand, for heterogeneous cases, since chi is 10 to the 6, not only in 3D cases, we are same as a Fetty, we get much higher accuracy. So at the moment, it's very tentative. We compute this guy and each processor, we don't really communicate. A does not need a communication. These guys do need a communication. In other words, the vector, iterate vector. So up to here, we don't need any communication. FB is the size of interface degree free. So this is all done in each processor. And then the vector size of the interface vector size is the one communicating to generate this vector. And this is a diagonal. So intercommunication and solution next iteration, we all do diagonal. This is diagonal, this is diagonal, this is a Boolean matrix, this is vector. It takes no time to generate that. This is process independent, no communication. And this is the one you need a communication, but only small size of vector. We are very encouraged knowing that for heterogeneous problem, DP seems to outperform the dual solution algorithms. So we'll see much work is needed, but we'll see how this thing will pan out. We are very optimistic. The third application is a really very important problem. Excuse me. In safety engineering, because some of this power plant, especially nuclear power plant facilities, are not really too far from where the people live. And if there's an accident, it's a real catastrophe. So you really want to monitor that 24 hours and either shut it down or before it gets bad, you repair that. And it's not France or South Korea's problem, it's worldwide. So here, this is a pathological problem that I came up with. You have this 1 degree freedom problem. I have here assumed that this is the way the damage occurred. as I showed you. So when you assemble this thing, suppose that this K3 changed. I mean, it doesn't really affect that much when you assemble. But when you see the partition, when K3 changes, you see right away over here. So that the power of unassembled system, how that can be utilized for damage detection. So I showed you this one yesterday. In fact, theoretically, when this thing is somehow in your conversion didn't come out, we can see, 90% is gone. You see the factor theoretically. But we did some experiment, okay? And so for that problem, we have a PD times K, and then when you assemble with that, on the thing, we have element 1, element 2, element 3, element 4. So once we identify this, just use assembling operator, you can demonstrate each element by element changes, mimicking experimental data. And this is experimental data you use. So this is the real life. So by changing the width of midsection beam to 10, 20, 30, 40, we wanted to test to see we can actually predict and localize the damage. So pretend the changing the width as a damage in the cases, as you see over here. Okay. Case where there's nothing, there's change and this is the experimental result. In experimental result in mode 1 to 3, you have healthy system, not so healthy, and blah blah blah. Usually changes. There are modal shape changes. From this, you cannot really, even for this simple problem, you cannot really pinpoint where the damage is. Okay. So most people do here is this is not KG, KD. This is not a mistake. KD, KD. KG means assembled. How to assemble the stiffness matrix from measure the data and reconstruct it, reduce order, reconstruct KG. 25, 50, 75. And you cannot really do at the element. You only look at the node. It's nodal quantity. Whereas in DP, it's an elemental quantity. So you can see the changes over here. Okay. Element 1, 39, 148, 97, element, and biggest change occurred in the element 2, which shows this is where the damage is. This is not from analytical data. This is from measured data we utilize. Okay. So one of the critics says, yeah, KC, that's only 3 elements. What about the multi-element? So we did multi-element, okay? And we put holes, little holes here. There's 1, 2, 3, 4, 5, 6, 5 or 6 elements. We put little holes at different locations, okay? And then we did testing and all that. And that's the view. And you can see in terms of frequencies, you cannot really see the effect of that hole. And this is again KD. And this one shows that damage occurred in case 1 is 42. Here, damage occurred in 11A, which is totally wrong. By looking at this, you see case 1, damage occurred in 6, and case 2, damage occurred in both 5 and 6. Even for small hole, when you did the experiment, carry that out using this DP localized damage algorithm, it really pinpoint out. So I'm very happy, and I'm really hopeful that this would make an impact in safety monitoring system. So since we are running out of time, let me just skip that. The last part, which is, I myself wrote some papers about reduced order model. So this is a partition, this is assemble. One nice thing is assemble the model shape, assemble the global frequencies are related by, this is partitioned model shape. This is partitioned velocity. I'm sorry, frequency. They are identical. First time I was quite surprised myself. Maybe I made some error or some miracle coincidence. It turns out to be this. This really got me real confidence in DP formulation as a dynamic system. If the eigenvectors are DP equations the same as assemble the system, I'm safe. Okay. Therefore, we don't need to go through choosing substructure 1, 10 elements, substructure 10 mode, substructure 2, 20 mode, substructure 3, 50 mode, nothing. This is it. Once you do, in eigenvalue package, you can have lowest 5, lowest 7, lowest 10 mode. You get it? You have eigenvector. You have reduced order model. Period. Not only that, it actually, we have a theory. From this theory, we can actually tell how much accuracy we're gonna get. This was never possible. So we used this one, trace over this. This is our stiffness. PS is M inverse time P. This one, trace of that is exactly sum of eigenvalues. Okay, frequency squared. Now we can shift to this guy and generalize inverse, and then that becomes 1 over sum of, another 1 over omega 1 squared plus 1 over omega 2 squared, etc. You know what lowest frequency has the largest weight. Second one is the second largest weight. So this gives you directly by truncating how many modes you get, exactly what accuracy you're gonna get. And this is an example. For example, if you use only 2 modes, you get the 94% of the system energy, and etc. So you have a confidence what accuracy you're gonna get. You don't have to worry about, subtraction 1 or 2, how many modes, no, nothing. This really is an innovative component model synthesis theory, basically. So this is a the thing that Craig Bampton used in famous 1965 paper on component mode synthesis, that is implemented in all conceivable finite element code. Okay, that Craig Bampton method. So we use exactly the same problem he used. What's nice here is he used how many more, depending upon how many more you choose, what accuracy you get. He spent all time for that. The reason is, depending upon how many modes for each substructure you use, the global model accuracy is changing. In our case, the global mode is a machine precision accuracy. We don't have any inaccuracy. It's just machine precision accuracy, period. Okay? So for that example, we plotted the 1 over omega square sum. And this is the typical thing you use in data-based modeling when you use the various techniques to extract how many eigenvalues you want to use. So we use like a 4, and we have about 99% accuracy. We don't care where that mode came from. It's a global mode. Okay. And we ran transient analysis where at one corner we apply the step load. This is global system using entire mode. And this one is using only first 4 mode. Okay. And our error criterion, mode selection criterion is validated. It's a linear algebra. Sum of a trace over a operator or matrix is a sum of eigenvalues. And if that is stiffness, then inverse of stiffness, sum of the trace is sum of 1 over omega squared sum. So we are very encouraged that the DP-based CMS algorithm alleviate time-consuming iterations choosing different number of modes for each partitions. Okay, and this, we believe this will make an impact on multiphysics reduce of the model. Okay, and we have to formulate the eigenvalue problem for using this DP philosophy for multiphysics problem, and we are working on it. And once we have that, all we have to do just the DP eigenvalue problem, and you have the model and model shapes for coupled systems. And I think that's it. This is the last one. Yeah, remember, displacement velocities are linearly independent.
The Hamiltonian formulation. Otherwise, it doesn't work.
Yeah, otherwise Hamilton would not have survived.
Okay, is there any question, comment? So thank you again very much for your presentation. I was especially interested when you mentioned in the quasi-static approach that you filter rigid body modes. So do you filter them a priori, or is it included in the methodology itself that
After you compute.
After you compute, so that they were.
Yeah. Because if I didn't know displacement, acceleration are linearly independent, I would not have come up with that. So It's very important to know some fundamentals, even in computational mechanics. Therefore, I had to satisfy different the displacement constraints. So in my case, I satisfy acceleration constraint and displacement constraint. Therefore, I satisfy two linearly independent variable constraints.
In the case of quasi-static, if the loads are not equilibrated, you should equilibrate them in order to get a unique solution, right?
In the quasi-static problem, it's very important that you get what we call fundamental solution. The fundamental solution in partition formulation means when each partition is floating, it's visible mode. Is the fundamental solution. So you get the fundamental solution T, which is in rigid solid. When you chop, you get forces transmitted without any deformation. Okay, and that force is the one you distribute. And then look at, okay, if the force is distributed, just looking at each partition, what kind of displacement would I get? And that, what that does physically is fundamental. If you apply load over here, I have 1,000 partitions. This guy will not be felt over here until you go through 1,000 iterations. And what that fundamental solution does is when I apply the load over here, by having that fundamental solution, I already transmit from there to there.
In quasi-static, that's essential, because otherwise...
Yeah, otherwise you're going to have many iterations. And then once you got that, every time when you have a deformation, that has to go down to this solution vector. And that's what the filter is about. Yeah.
Very interesting. Anything else? Any other question? Or if not, thank you again. Can you see from me?